Okay, hello my dear friends. Today in this video I would like to tell you a part of the chemical bonding the chapter. In this video I would like to tell about the sigma bond and pi bond, a very prescribed definition, and after a few minutes you would be able to differentiate between p pi d pi and d pi back bonding in their different types of molecules. Okay, let's take a quick review. Sigma bond. I'm just writing a very simple clear cut definition. Sigma bond. Sigma bond is a bond in which there is a coaxial overlap takes place between the s orbitals. Okay, and in this, these are the type of orbitals in which coaxial overlaps takes place. That means the overlap is along axis and it will give a compound like this something to infinity type of structures are just embedded to each other. And in pi bond the direct definition says that the collateral overlap occurs over here, and in this a figure of 8, two figure of 8 will be interacted collaterally, and it would represented like this is a collateral overlap. Although these type of definitions are very much specified in our books. Now let's take a review. That's what about I was talking. That means firstly we will talk about p pi. I'm not going to define the p pi d pi back bonding. I will just tell a method to tell how would you identify the compound, whether it is in which type of bonding. Okay, let's take an example as oxygen has no vacant d orbital. I'm telling the quick method. Okay, so focus over here. Oxygen has no vacant d orbitals. Yep. And it and let's take another element is sulfur has vacant d orbitals. Now take a look over these two elements. Oxygen exists in second period. Oxygen is present in second period. Okay, and sulfur is in third period. Okay. Yep. And now take example of the compound which has these two types of elements. Let's take sulfuric acid, H2SO4. H2SO4, and in this type of compound you have to figure out that which type of bonding is being taking place. That is a p pi d pi or d pi p pi. Let's draw its structure. Okay, I'm just drawing its structure of H2SO4, a clear cut structure. Okay, now look over here. There are two bonds. In each sigma bond there are two electrons. Okay, now focus over here. This sulfur and this oxygen, these two bonds, sulfoxy bonds, these two sulfoxy bonds are similar. Let's focus on each side separately. This sulfur has 3d vacant orbitals. 3d vacant orbitals. Okay, and this oxygen has 2p orbitals. Yep. And these two electrons, there are two electrons. Okay, there are two electrons in these two bonds. And now after looking at this, there are 2p in oxygen and 3d vacant orbitals in sulfur. So this pi bond will gonna represent p pi d pi back bonding. This pi bond, p pi d pi back bonding, since p orbitals from oxygen and d orbitals from sulfur, and similarly over here in this bond p pi d pi back bonding. So if a question in this type of molecule asks that how many types of p pi d pi Borbach bonding takes place, your answer will be 2 p pi d pi bonds are present in this molecule. Now talk about how. Now take a look at how a coordinate bond is formed in this compound. How a coordinate bond is formed in H2SO4. Okay. Okay, let's take sulfur. Sulfur. Sulfur's elec Sulfur needs two more valence electrons. Two more electrons to complete its noble gas electronic configuration. Okay, as we have already read in valency. Let's draw a quick structure over here again of H2SO4. Okay, I'm not representing pi bonds over here just for the sake of simplicity. Okay, look over here. Look, please come in the prescribed earlier figure. There are two bonds over here, and if we are, yeah, it's just a trick, not a prescribed method in our books. It's just a trick that I'm gonna tell. Okay, these two bonds, sulfur needs two more electrons to complete its vacancy. Okay, and these two electrons, this electron and this one, will come with sulfur. Okay, that means sulfur's valency is completed now. There is no need of these double bonds. So for as sulfur has completed its audacity, we will put up this arrow where this is also a type of sigma bonds, and these sigma bonds are known as coordinate bonds or dative bonds. Okay, these two are coordinate bonds. Similarly, these two are coordinate bonds. This is just a very simple method. Let's take another example to make the picture more clear. Okay, I am taking P4O10 as another example. P4O10. Okay, okay, let's draw its structure. P4, P4O10. It's just a trick. It would be helpful in the examination since the time pressure, time constant has to be managed very precisely by the students. And I hope this method will suit you. Okay, this is a P4O10 structure. Okay, now take a look at how many p pi d pi, or which, firstly we have to take that which type of bonding is taking place, whether p pi or p pi d pi bonding taking place over here. Okay, as prescribed earlier, oxygen has two p orbitals, as I've already told you, two p orbitals, and p phosphorus has which type of vacant orbitals? It has 3d orbitals. 3d orbitals, vacant orbitals. Okay, 3d vacant orbital. Similarly, as the previous case, if you focus on this bond, PO, this bond, PO bond, again P, two P's oxygens p orbitals and sulfur's phosphorus d orbital. That represents p pi d pi, p pi d pi, and here pi is being put over here because these double bonds represents pi, p pi d pi. So if you take that, there are 1 2 3 4 total number of 4 p pi d pi back bondings are present. 4 times p pi d pi back bonding is present in P4O10. Okay, now let's take that number of coordinate bonds. How many number of coordinate bonds are present in this compound P4O10? Coordinate bonds. Okay, as I've already told you earlier, firstly we have to check the phosphorus. Phosphorus has 15 as its atomic number. It needs 3 more valence electrons to complete its vacancy for the noble gas configuration. Okay, 3 more electrons being needed by phosphorus. Okay, let's draw a zoomed structure of that compound. I'm not drawing the complete structure. One, we simplify our task. Here are two electrons, two electrons in a single bond. Okay, okay. Now phosphorus needs 3 more electrons. Let one electron from over here, one from over here, one from over here. Okay. Now 3 electrons are jumped towards phosphorus, and now it seems that there is no need of this double bond. Okay, the single bond can work out over here properly. So as a resultant, we can also say, oh, the structure this side is similar. Will put a sigma bond called new sigma bond, also known as coordinate bond or dative bond. Okay, this is dative bond or coordinate bond. This is okay. So if we look at the structure P4O10, 1, 2, 3, 4, there are total 4 coordinate bonds are present. Therefore, total 4 coordinate bonds are present in P4O10. I hope this video will help you. And if you have any query, you can ask in the comment section, please. And you can also take a quick review of this whole theory since it's helpful during the examinations. Okay, thank you.